Okay, so this is topic 3 and 13. So all about the periodic table and different groups on the periodic table and characteristics of groups and periods on the periodic table, including trends and things like that. And so that's going to be the main focus on this. And while it's not a huge amount of material, hopefully we can discuss different ways for you to kind of minimize what you have to memorize on this stuff, because I think there are things that you can do to help ease how much you have to retain memory-wise to be able to solve all these types of problems. The first thing we want to establish here in this unit is understanding the periodic table and understanding the labels of the sections of the periodic table and things like that. And so if we're looking at a periodic table here, okay. Let's see, I'm going to try to draw this.
How much will we annotate this?
Wait,
should I make it pretty big?
Yeah, make it a little big. Okay. I won't write as much in there, so probably maybe just make it like 8 or 9 lines. Okay. So periodic table here. Okay. A couple of things that I want to highlight on here. Okay. First, there are certain important groups that you need to know for this periodic table. Okay. So there is the alkali metals. There are the alkaline earth metals. I don't like the way this is writing. I'm just going to write like this. The alkali metals. The alkaline earth metals. Group 17, the halogens, and group 18, the noble gases. Okay. The middle section here, the transition metals. And we'll dig that a little deeper into that in higher level section of this. And then underneath this all, there's 2 rows. Okay. Okay. And these are known as the lanthanide and the actinide series. Okay. You don't really need to memorize those because here's a hint. They're called that series because of the first element in each row. So the lanthanide series is called lanthanide because the first element of that row is lanthanum. And the first element in the second row is actinium. So like that should help you kind of identify which one's a lanthanide, which one's the actinide series here in that order. Okay. So identifying these groups are important just for kind of general knowledge here. Maybe it's a multiple choice question. Most likely it's a multiple choice question, just identifying parts of the periodic table and things like that. Okay. Now, yes. No, you do not need to. Well, you need to know the general position of them, but oh, it does say show the position of metals and metals. So, yeah, your metalloids are kind of in that stair step right here. Okay. I hope I didn't. I might have done too many rows here. One, two, three, four, five. I think it's okay. Your metalloids are the ones kind of right, the stair step between the metals and the non-metals. So everything left of the metalloids are the metals. Everything right of the metalloids are the non-metals. And these rows that we have on the periodic table are our periods: 1, 2, 3, 4, 5, 6, 7. And the numbers on the top are our group numbers. Okay. Elements in the same group have similar properties, similar chemical and physical characteristics. Elements in a period have trends that they behave in, but they don't have similar characteristics. And so just remember that the periods you read across, even though the numbers are written vertically, and groups you read vertically, even though the numbers are across. Sometimes students have struggle with that. The second thing you want to keep in mind in regards to the periodic table is how it helps you with electron configuration. Because the periodic table is actually organized in a way such that you can use it to determine the electron configuration of substance, because these two groups over here, and I guess helium over here, represent our S sublevel. So two elements wide because each element represents an additional electron, and an S sublevel can only hold 2 electrons because it has 1 orbital. Over in this section, you'll notice that it is 6 wide, which represents the P sublevel. Okay, so every element you go to the right in that section, you add an additional P electron. Okay. In this section here, this is your D sublevel. Okay. What you have to remember about that D sublevel is it is always n minus 1, meaning that whatever row the D sublevel is actually on, the energy level of that D sublevel is actually 1 less than that. So I guess actually my drawing is not very good here now that I think about it, because like there should be 2 rows of, like there should be another row up here, because the D sublevel doesn't start till row 4. That's kind of my fault then. Okay, so the D sublevel on the 4th row is actually the 3D sublevel when you're writing electrical configuration, and the D sublevel on the 5th row is actually the 4D sublevel. So just keep in mind that it's 1 less for the D, but for S and P, the number stays the same. So S and P are always on the row that the appropriate row. Down here is the F sublevel. Okay, 14 electrons wide, meaning 7 sublevels. And remember, the period the element is on, that's the energy level the valence electrons are located on. Okay. So if you have an element on the 4th period, then all of its valence electrons are in the 4th energy level. So 4s and maybe 4p. But D should never be on the valence shell. Remember, the groups also help you tell the valence electrons. So group 1 has 1 valence electron, group 2 has 2 valence electrons, 13 has 3, and then 4, 5, 6, 7, and then 8. So keep that in mind as well. questions so far about anything I'm diagramming here?
What is the hyphen
F sublevel? Yeah, so it's S, P, D, and F. So S has 1 orbital, 2 electrons. P has 3 orbitals, 6 electrons. D has 5 orbitals and 10 electrons, and F sublevel has 7 orbitals and 14 electrons. You're never going to have to do electron configuration for F, because there's still some kind of debate on how you actually do the electron configurations for those. So the IB doesn't even go in there. So the IB won't go past 54, which is like the last, like I think it's XE, which is the like last row before you start involving F. So you'll never have to worry about F. Okay. Questions?
Oh, there's one where there's an exception in like the D sublevel. And I remember there was one IB question where you said they would ask you it because it makes you think of like several different things. What question was that again? If you remember.
Yeah, that was copper +1. And so copper +1, you have to know that it's an exception, that it's 4s1 3d10. And then it is, when you lose the electron, you lose it from 4s. And so it ends up being just AR 3d10. So that's the exception for that one.
Okay.
Yeah, you'll see that on the topic 2 and 12 review on there for exceptions. Give me 1 second. I need to pause recording. So the chromium copper exception is the fact that even though you read the electron configuration, if you read it the right way, it ends up being AR 4s2 3d4, and copper is read as AR 4s2 3d9. But that's not the way the actual electrons are occupying, because to add stabilization, one of the electrons from the 4s goes into the 3d so that it can become a half-filled or full. So the proper electron configuration for copper is AR 4s1 3d10. And when you lose an electron from that, you lose from the 4s first. You always lose from the outermost shell first, even if it's not the last one you write. It's the outer shell first. So the 4s go before any 3s. And so what Latifa was referring to was that when you lose an electron here, it ends up being AR 3d10. And if you don't know the exception for copper and you don't know how to lose electrons from the right place, then you can't get it right. And that's why like they do this one most commonly, because you have to know both things to be able to get it completely right. If you don't know one of those two things, then you can't get the right answer. And so that's the challenge with that. Yeah. Yes, it becomes 3d9. But the reason why they don't do that one is because even if a student didn't know the exception of copper, they would still end up with 3d9. Like, so like, even if they did this one, like here, if they thought it was this and they did Cu2 plus and they knew you lose from 4s, they could still somehow get the right answer, and the IB doesn't want you to be able to do that. So that's why they usually use copper +1. All right. Other questions about that? And yes, the more in-depth orbital and sublevel theory and electron configuration stuff is all in topic 2 and 12 review video that we did. I think it was the first one we did in January. So if you want to look back at that and skip to that part, then I strongly suggest, encourage that, I should say. Okay. The big thing about this unit is really periodic trends. Now let me scroll it up here in case people are still writing. Okay. Periodic trends. Explaining how, generally speaking, elements behave as you go across the periodic table and as you go down a group. And so when I'm talking about trends, I don't even talk about trends first, because the trend is a result of a characteristic of an atom or an element based on how what's positioned on the periodic table. So whether it's atomic radius, ionic radius, electronegativity, ionization energy, it's all related to the same reasoning for all of them. And so that's what I start with when I'm explaining this, because I start with the reasons and then you just apply them to each trend and then get the answer for you. Because the IB is never going to ask you if something increases or decreases across the periodic table or down. They're going to ask you, why does it do that? And that's the core thing. And that's how, again, how you minimize what you have to memorize. Instead of memorizing the trend for every single, like across the period and down the group for every single trend separately, it's just the same two reasons for all the trends. And you can apply them whenever you need to get the right answer. And so instead of memorizing 15 pieces of information, you memorize 7. And that's half the amount of memory you need to exert. So here's what I want you to think. As you go across a period, okay, so let's say you're going across period 3 from sodium all the way to argon, Ar. The characteristics about those elements are, 1, they have the same energy levels, okay? So every element in period 3 has 3 energy levels present. So that is not a differentiating factor between the elements in that period, okay? But what they have different is an increase in protons, or what we call nuclear charge, okay? Because as you go from sodium across to argon, you gain 1 proton every step you take to the right. And instead of thinking as protons pulling on individual electrons, protons pull on the entire atom as a whole. So they don't just pull on 1 electron at a time. What they do is they pull on the atom as a whole. And what that means is, even though you're gaining a valence electron as you go across, that electron's still in the same energy level. And therefore, it's not going to affect the trends as much then, as opposed to the increase in protons, okay? And so this increase in protons or nuclear charge creates a greater attraction for the energy levels, okay? So as you across the periodic table, the more protons you're gaining in the same energy level, has to be the same energy level. You can never compare, you're not really supposed to be comparing diagonally. It should be 1 constant and 1 variation. As you go across the same period, you have the same energy levels, but that additional proton is creating more and more attraction. Yes, Emma. I think generally speaking, yes, that's kind of lumped in with the same energy levels, because the repulsion can vary a little bit as you gain or lose electrons in the valence shell, but yes, I guess generally speaking, the repulsion is about the same for all of them. Okay, so you want to key on the fact that as you go across period, the fact that is the attraction is getting greater because you're increasing the nuclear charge and the energy levels are the same. As you go down a group, now what's happening is you have about the same nuclear charge, but you have different electrons. And what I mean by same nuclear charge is this, to clarify. When you look at lithium, sodium, potassium, and like rubidium, they're in the same group. They're all in group 1. Well, lithium has 3 protons, and they have 2 electrons here, and then 1 electron, 1 valence electron out here. And sodium has 11 protons, and then it has 2, 8, and then 1. So even though you're gaining protons, the fact that you're adding energy shells negates that additional number of protons that you're gaining. So effectively, lithium, sodium, potassium, rubidium all have essentially one proton pulling on that one electron on the outermost shell. So the same nuclear charge is present there because the inner electron shells cause shielding. Oh, sorry, I wrote different electrons because I didn't mean electrons. I meant energy levels. I was already thinking ahead, sorry. That's my fault. I was already thinking about the diagram and I wrote what I was thinking instead of what I intended. So different number of energy levels. So the same nuclear charge because of the inner shells. When you have a different number of energy levels, you have more shielding from the inner shells or levels, which means a weaker attraction. Okay. So although lithium has one effective proton pulling on its outside shell, and sodium has one effective proton pulling on its outside shell, the fact is that sodium's inner electrons here block some of that attraction from reaching that one electron. So it's going to be weaker than the lithium attraction for its valence electrons. So the inner shells shield that attraction from reaching the outermost shell. So there's a weaker attraction present here. And those two concepts explain every single trend. The general trend, I should say. There are exceptions that we can talk about, but the general trend fits in both those. All you're really talking about in every single trend is attraction. Are you getting more attraction? Or are you getting less attraction? And what does that mean for each trend? So once you have these two concepts down, whatever trend they give you, you can apply these concepts when necessary. So don't memorize increase and decrease and stuff like that, because that's never going to be the question. It's going to be why does it increase or decrease? Questions about that? Clarifications? Yes, Sammy. Yes. Right. For the added protons, you mean? Yeah. So we call that effective nuclear charge. So the effective, like the actual attraction is one proton for that one valence electron in all of group 1. And in group 2, it's 2 protons for the 2 valence electrons in group 2. In group 17, it's 7 protons for the 7 valence electrons in group 17.
So you also explain the shading part?
In the bottom here? Yeah. So while it is still 1 proton for 1 electron, that electron is A, further away, and B, also still shielded by more and more inner layers to protect the attraction from reaching all the way out there. So this electron here is held more weakly than this electron in this element. Because A, it's further out, and B, the shielding of the inner shells prevents the attraction from the one proton from reaching that shell as that electron as effectively. So weaker attraction. Does that make sense, Sammy? Okay. Okay. So when we start talking about trends, you'll see you just apply these concepts. And so remember these two concepts. These are the main ideas that you really want to think about. And then you can apply them to everything else instead of talking about every single one and then memorizing every single individual trend, because the odds of them asking about more than one trend is very unlikely. So you're essentially memorizing 5 trends and 15 ideas for a lot less usefulness than really is expected. You got to be efficient about that. Okay. So first trend, atomic radius. Okay. What did I do? Purple and blue. Okay. as you go across a period, what should happen to your atomic radius? Yes, Sammy. I'm sorry. Why decrease?
As we go into closer to adding more protons to it, so we get a flexible attraction from that and more protons.
Exactly. So the fact that you have the same energy levels, but you have the increase in protons, then the radius gets smaller. Okay. So again, like Sammy said, he was just applying the concept to this to rationalize the reason why atomic radius goes across, gets smaller as you go across. But again, the IB is never going to ask you what does atomic radius do as it goes across the period, because on the short answer, you have all the atomic radii. So why would they ask you whether it increases or decreases if you've got all the values in your data booklet already? So they would never ask you that. They'd be asking you why. As you go down a group, what should happen to the atomic radius? Increase. Why, Alexandra? You have additional energy levels, right? So you have additional energy levels. So therefore, it should increase radius. Ooh. I think if they were comparing elements in the same group, it wouldn't hurt to say that, Emma. Yes. So I guess yes, you would say same nuclear charge here as well. Yeah, that's a good point. Second trend. Ionization energy. Okay. So ionization energy is, and this is, I guess we're going to talk about first ionization energy here, is the energy it takes, or the energy required, to remove one electron from an atom in gaseous state. So it would be something like this. That's the reaction for an ionization energy. Not to be confused with like oxidation or reduction. Well, actually, I guess you could actually no, it would be argued. You could argue that's an oxidation reaction, but it's really you're putting energy into it instead of like a chemical reaction happening. Okay. So we're talking about how much energy it takes to lose an electron. So what we're really talking about is the attraction the atom has for its electrons. Again, because the more attraction you have, the more energy it takes to remove the electron. So again, going back to your concepts here, in these two explanations, as you go across a period, your ionization energy should increase because you have greater nuclear attraction. Oops. For the same energy levels. Because a greater nuclear charge means a greater pull on the valence electrons, which means it's harder for you to remove an electron from that atom. So again, we're being very repetitive here, and so that's why I'm saying don't compartmentalize every periodic trend because they're all sharing the same concept. Be efficient. as you go down a group, okay, the ionization energy decreases due to a weaker attraction because of you have the same nuclear charge, but an increased number of energy levels, which increases the shielding, which makes the attraction weaker. Questions so far? Any clarifications? Okay. Third trend. Electronegativity. Okay. The attraction an atom has for a shared pair of electrons. So essentially, how much is that atom pulling on a shared pair of electrons or a covalent bond? And this is like a relative scale, by the way. The electronegativity scale is a relative scale with respect to each element. It's not an actual measured value that like it's based on something. It's just comparing them when they're bonded to each other. So when you go across a period, what do you expect the electronegativity to do? How is the attraction going to change as you go across a period? It's going to increase. So electronegativity increases for all the same reasons. More nuclear charge, same energy level. So the nucleus itself is the same distance from the shared pair of electrons that are bonded to. So the only difference is how much is the nucleus pulling. And with more protons, it pulls on that pair of electrons more and more and more. As you go down a group, the attraction weakens, therefore, the electronegativity decreases because you have more and more energy shells, which means the nucleus is further away from that shared pair of electrons, which means it has weaker attraction for it. Which makes sense in the periodic table because what's the most electronegative element on the periodic table? Fluorine, up in the top right. What is fluorine's characteristics? It has the highest nuclear charge possible, 7. Well, other than noble gas, because noble gases don't bond for the most part, so we don't count them. Has the highest effective nuclear charge of 7, and it's the smallest radius of all the elements that are eligible. So that's why it has the highest. And francium, down here, has the lowest, because it's the largest atom with the weakest nuclear charge, and therefore it has the weakest attraction an atom has for a shared pair of electrons. So that information confirms our reasoning here. Questions? Yes, Mateo. Oh, the values of electronegativity that we see like on a periodic table and stuff like that, Mateo, they're relative numbers. They're not like kilojoules or like joules, like other numbers, they're relative to each other. So like fluorine's 4, and hey, Mr. Odin, how's it going? Good, good. How are you? Yes, these are the Chem Saturday Session Warriors. Yes, sir. Yeah, Sam. Oh, goodness. Thank you. Thank you, Mr. Odin. Oh, goodness. They did not come here for a photo op, Mr. Odin. I don't think they're. Oh, my goodness.
Mr. Trong, what time are y'all gonna start topic 13, do you think?
I would say probably about 12:15.
Okay.
Oh, there's about 6 or 7 out here on the Zoom call as well. So Mr. Oda says hi.
Good to see those names.
Yeah. You want a donut, Mr. Odin? You want a donut? I brought the donut.
Nah, man, I'm old.
Oh. I forgot all this is on the recording, so this is gonna be awkward. But so, yeah. So Tifa, I would say about 12:15 because we've got a couple more trends and some reactions you need to know and stuff like that. So maybe about 30 minutes.
All right, thanks.
You're welcome. Okay. So periodic trend 4. I'm gonna be honest with you, I don't like these last 2 trends here as well. Okay. And so because they're not as particular as the rest of them, okay? Because they don't necessarily make as much sense with ionic radii and stuff like that, but and electron affinity, but I'm gonna still group them in here as well. Okay, because I would know the definition of those trends as well. Okay. Electron affinity is the energy change, energy release when an electron is gained by an atom in gaseous state. So I would definitely know these definitions because you're going to have to apply them. But the values of this is more useful and higher level when you do Born-Haber cycle and things like that. But so this looks like this. Okay. Where the atom gains an electron and becomes a negative ion. Okay. And so you'll still see the same idea that as you go across a period, generally speaking, electron affinity increases. Because those atoms with more and more valence electrons have a greater attraction for electrons, and gaining an electron actually provides it more stability. So that attraction coupled with the number of valence electrons as well increases the amount of energy released when it gains an electron. And as you go down, the electron affinity decreases. Because as you get bigger and bigger an atom and you have more and more electrons, the addition of an electron benefits it less for stability. Okay. So down a group, the electron affinity decreased. Yeah, with that, it's a bit of the attraction for the nucleus, but also the fact that you're gaining more and more valence electrons as you go across. So you're getting closer to an octet every time you gain an electron. So like the halogens have the highest electron affinity because by gaining one electron, they become super stable, and so they release a lot of energy. But electron affinity as a trend, I don't really love, and I think that's not one that they're going to really talk about that much. But I would still know what it is. The one that I really don't like is ionic radius. And so I'm going to approach ionic radius differently than the other trends that we talked about here, because if they're talking about across a period, for the most part, it kind of follows the same trend of the atomic radius. But really what they're talking about here for trend is comparing elements that are similar in characteristics or even elements versus their own ion. So when I think ionic radius, I'm comparing one of two situations. I'm either doing the atom versus the ion as one example. So we'll do that first. So the first thing you might do is ask you to compare, like for some example, magnesium versus Mg2 plus. So Mg versus Mg2 plus. Now, when you're trying to explain this, I look at the protons and the electrons. Mg and Mg2 plus both have 12 protons, but Mg has 12 electrons and Mg2 plus has 10 electrons. So which of those species is going to be smaller? Which of those two species is going to be smaller? Wait, which one? Mg2 plus. Because you have fewer electrons with the same attraction, so it's going to pull it in more tightly. And so this is going to be smaller. And it's also you're losing electron shell as well, because you lose the two valence electrons. So this one's going to be smaller. Okay. Conversely, we look at F versus F minus. Well, F has 9 protons and F minus has 9 protons. F has 9 electrons and F minus has, 10 electrons. Okay. So they have the same attraction, but now you have more electrons here. And this is kind of back to what Emma was saying earlier. When you have more electrons, they repel each other more. So they force themselves to spread out. So therefore, this one ends up being, the ion ends up being larger because you're gaining electron repulsion. So I think with ionic radius, if you're ever comparing an atom versus ion or ions with each other, the thing you want to do is ask yourself, how many protons and how many electrons do each of these things have, and then compare them that way. Because I think that's the best way to approach it. That's one way to compare ionic radius. The second one is isoelectronic ions. Okay? If you remember from root kind of terms, iso means same. Electron means electron. So isoelectronic means you have the same electrons as each other. So what does this mean? Something like this: Mg2 plus, F minus, O2 minus, Na plus, and Ne. Yes, Mateo.
I mean, it would be difficult to compare them with
That's a good question. Okay. They're either going to be isoelectronic with each other, all of them together, or there will be some that are isoelectronic with each other, which allows you to eliminate some of them. So like, let's say you're looking for the largest atom, ion, and 2 of them have 18 electrons and 2 of them have 32 electrons. Well, you can eliminate the 18 ones right away because the 32 by default are always going to be bigger. And then you compare those two with each other. But no, they won't give you like different ions all over the place with different number of electrons usually. Tess. Yes, because we're just going to write a little bit under here. Because even with isoelectronic, you do the same thing. Write out how many protons and electrons each one has, and then you can order them from smallest to largest. So magnesium has 12 protons and 10 electrons. Fluorine has 9 protons, and 10 electrons. Wait, what's up, Emma? Yeah, sure. Yeah, an atomic radius is the distance from the nucleus out to the valence electrons here. Ionic radius is also that, but now you've gained or lost electrons, which affects the radius itself. Yes. Yeah. So ionic radius is usually dealing with the ions of the elements here. So one of two scenarios. One, you could be comparing your atom versus its own ion, like up here, or you could be comparing a bunch of ions to each other. But when you do that, usually they have to have the same valence electrons before you can like compare them. You're welcome. So that's why I say, if you're trying to compare ions, the first thing you do is write out how many protons and electrons each has. Because you can either A, eliminate ones, or B, go, oh, they all have the same number of electrons. That doesn't matter. What does matter is the protons here. So which of these is the smallest ion? Mg2+, because it has the most protons, pulling on the same number of electrons. So this one will be the smallest. And then it'll be Na+, and then it'll be Ne, and then it'll be F-, and then O2- will be the largest of these ions. Are you gonna be able to fit that there, Cass? Okay, so Mg2+ is smaller than Na+, is smaller than Ne, which is smaller than F-, which is smaller than O2-. So yeah, if you're talking about ionic rays, I think the best thing for you to always do is write out all the protons and all the electrons of every species that you're comparing, and that should tell you, instead of memorizing, oh, cations are always smaller than their atoms, or anions are always larger than atoms, just write out the protons and electrons, and you can figure that out on the fly. Minimize what you have to memorize and apply reasoning and logic, which I think all of y'all are capable of doing. Please don't prove me wrong. Okay. Questions about that? Yes, Daphne. They would never do that. So it wouldn't be as close as 11-. There might be one that has 18 electrons, and that would be larger than all of these, no matter what. But no, they would never do 11 electrons in this group. Because that's, again, remember, every time the IB wants to compare things, something has to be the same and something has to be different. You can't have everything different because then there's too many factors in your deduction. So no, you wouldn't like get Na thrown in there by itself with 11 electrons and 11 protons. That would be difficult to compare. Yeah. Okay. Okay. Questions? Mateo, you good? Okay, I thought I saw your hand up. That's why I just, okay. Now, metallic behavior. Okay. This is a little bit with trends, a little bit. This is kind of an afterthought of trends here. So metallic behavior. Okay. Metallic behavior is how much an atom behaves like a metal. And what that means is, how good is it at losing electrons? Okay, because metals tend to lose electrons. So the ability for an atom to lose an electron determines how much like a metal it is. Okay. So really, what trend does metallic behavior line up with? First, ionization energy, exactly. So the relationship between ionization energy and metallic behavior is direct. The more metallic something is, the better it is at losing electrons. And so group 1 metals are the best at losing electrons, hence why they're the most metallic metals on the whole periodic table. So you want to think of ionization energy, because you want to think metals want to lose electrons. So how do we characterize how good it is at losing electron? We measure how much energy it takes to lose an electron in the form of ionization energy. Non-metallic behavior wow, my handwriting is getting really bad here. Okay, is gaining electrons. So that has to do more with electron affinity. And so the most non-metallic elements are ones that can gain electrons the best, which is the group 17, or halogens. So those tend to be the most non-metallic in the whole periodic table. The halogens, the ones with 7 valence electrons. So it is very beneficial to gain an electron there. Oh, group 1, alkali metals. You're welcome. Okay. I'm going to skip the group 1 and group 17 properties and stuff like that for now, because I want to focus on the last kind of major thing, and that's the reactions of the reactions. Okay. And so one of the things you have to know is the general trend of certain characteristics as you go across a periodic table, especially period 3. So this section is labeled period 3 oxides. Okay. And so period 3 oxides are useful because as you go across period 3 bonding to oxygen, the trends of characteristics is very predictable and applicable. So you see the whole gamut of properties. And so what we're talking about here is Na2O, MgO, Al2O3, SiO2. See, P4O10, SO2, SO3, then Cl2O are your big ones. This table is not super long. It's only about 3 characteristics here, or 3 or 4 characteristics. So don't take a whole page for this. Okay. So understanding how the metallic behavior and non-metallic behavior affect how these things behave. And so the first thing is we're going to do bonding. Okay. So when a metal bonds with an oxide, what type of bonding occurs? When a metal bonds with an oxygen, what type of bonding occurs? Ionic, yes. It's not a trick question, y'all. Okay. Okay. Now, SiO2 is a unique substance which is giant covalent or network covalent. So it's a network of bonds and there's no individual molecules that exist. It's just this giant network covalent substance. And the other ones here are all covalent. So notice as you get more and more non-metallic, you stray toward covalent bonding versus ionic bonding. So that's an important aspect of this. Okay. Okay. Conductivity. Okay, this relates to bonding as well. These ionic ones, they are yes, but only in aqueous, liquid, and gas form. Because remember, you need free ions to be able to conduct electricity. Okay. And these covalent ones have no conductivity. As a pure species, I should say. Yeah. The next one is pH. Okay. These end up being, actually, I'll just write basic. Basic Al2O3 is amphoteric. SiO2 is slightly acidic. And then the rest are acidic. Okay. So again, notice the trend that's happening from one to the other. It goes from ionic to covalent. It goes from conductive to non-conductive. It goes from basic to acidic. Now, so I'll give you all a second, and then I'm gonna highlight something here. Some of these reactions you do need to know related to the pH of these systems. The reactions you need to know are for Na, Mg, P4, and SO2/SO3. Can y'all see what I highlighted there? I didn't realize the gray was so hard to see. So we do need to know those reactions. So this kind of follows along lines of metal oxides. React with water to form metal hydroxides. Same idea with magnesium oxide. Reacts with water to form the metal hydroxide. P4O10 or P2O5 reacts with water to form an acid, namely H3PO4. I believe it's 6 and 4 is, yeah, correct balancing. So yeah, you do need to know these reactions. They are going to expect, yes, Mateo?
You wrote, let's see, SO3 and SO2, but I feel like there was another one that had another variation. Like, last year I think we had like,
P2O5. Yeah. They behave the same way though. So yeah, P4O10 and P2O5, and then SO2 and SO3. Oh, it's just those are the common bonding, most common bonding structures of those oxides. No, that happens with the kind of expanded octet, because actually Cl does, but we're not going to go into those details. Phosphorus and sulfur tend to be the most commonly talked about, like multiple species. Okay, your SO2 forms H2SO3. Your SO3 forms H2SO4. Oh yeah, it's the same thing. P2O5 plus water still makes the same thing, H3PO4. I think it just now is like that. Yeah, it's just 3 and 2 instead. Because the oxidation number on P for P2O5 and P4O10 is the same, so it should make the same product. That's why the SO2 and SO3 behave differently, because they have to keep the same oxidation number, so that's why it makes H2SO3 and H2SO4. But those two are fairly easy because you just mash them with water together, and that's your overall species. So less needed to memorize SO2 and SO3 than it is for like these first 3 here. Like I would know those reactions. That's a common question. They would just say Na2O reacts with water. Write the balanced chemical equation for it. State, predict the pH of the solution that's formed when it dissolves in water. So you'd have to say like 11 or 12 because it'd have to be basic, right? Because you're making NaOH. Yeah, they might just say state whether the solution is acidic, basic, or neutral, or something like that. So that's, yes, that could be a very well 1-mark question. Write the balanced equation of sodium oxide with water. Okay. Okay. Other reactions that you need to kind of know as well, stated kind of here. Don't forget that NO2 with water forms HNO2 and HNO3. That's that acid deposition one that you need to know. And other reactions you should know that aren't related to period 3 oxides include alkali metal with water. So alkali metals with water always produce the hydroxide. So you have Na plus H2O, it produces NaOH plus H2 gas. So it always produces hydroxide and H2 gas as a byproduct. Next, alkali metal with the halogen. That's just synthesis. Okay, so like sodium and fluorine make sodium fluoride, and you have to balance it. So it's just synthesis at that point. But remember, halogens are diatomic, so when you write the reaction out, you can't just write F, you have to write F2.
The alkali metal with water are equal to last reaction. You said that they're not for that base, right?
No, they are for this unit. They're just not related to the period 3 oxide chart like we were doing earlier. But these are reactions you do need to know for topic 3. Oh, it's just the reactivity of group 1 metals with certain things. So they focus on group 1 and group 17 because they're the most metallic and most non-metallic substances on periodic table. So they're the most predictable and they're the most obvious. They have the most obvious chemical and physical properties of them. The last one is halogens with halides. Because remember, halides are the ion of a halogen, and a halogen is an element. So you might see something like this. F2 plus NaI yields NaF plus I2. So that's that single displacement. And you have to remember that F is more reactive than Cl, which is more reactive than Br, which is more reactive than I. So this is kind of like an activity series from topic 9 and 19, where F can replace all of them, Cl, Br, and I can't replace any of them. As an aside, sometimes they just write it like this, because that's really all that's changing. So you can see it both ways here. Halide is the halogen ion. You know, like how oxygen is oxygen and then the ion of oxygen is oxide? That's the same idea. So a halide is just the halogen ion. So F is fluorine, or F2, F minus is fluoride. Kind of with the naming convention that we, with ionic bonding and stuff like that. That's why they call them halides. Okay. All right. Questions about that? Oh, the NO2 one?
Yes.
That was just another reaction with water that produces acids that you need to know. It's not in period 3 oxide, but they say here, it says, oh, let me read it. It says, construction of equations to explain the pH changes for reactions of Na2O, MgO, P4O10, and the oxides of nitrogen and sulfur with water. So that's what we're doing here. Okay, that is the end of SL chemistry. And so we're going to take about 5 or 10 minute break, and then we will go into topic 13, which is new for HL. So thank you, SL students. I will see you later. I'll see you on Monday. HL students, just take a 5 or 10 minute break. All right. Okay. So this is higher level, topic 13. So we will review this again after mock exams. I know some of y'all are curious because you're trying to get all the information as much as you can. And so I'm going to offer it to you now. It's actually not as bad. And so the idea here, this is called transition metals. And it's really focused on the properties of transition metals and how they behave. So what we need to first establish is the properties of what are known as transition metals. Because not every element in the D block is a transition metal, even though we've generally grouped it that way because they don't actually fit the characteristics of transition metals. Okay, So things that transition metals have. This kind of these characteristics. So one, a transition metal has to have variable oxidation states. So you should need a Roman numeral when it's bonding with something. Okay. It forms colored compounds. So when it's ionically bonded with something, it can form colored compounds. Okay. 3, a lot of them display magnetic and catalytic properties. So they act as catalysts in here. Okay. And they can form, complex ions with ligands. And we'll talk about what ligands are. I think we might have mentioned it before, but so. Ligands. Sorry, let me clarify. Ligands. Yeah. Okay. So we're going to focus on a couple of these ideas and explain kind of what they mean. And so I'm going to focus right now on forming complex ions, magnetic properties, and variable oxidation states. And so the thing you want to focus on here for variable oxidation states is that you have a partially filled D sublevel, okay? Which means that a transition metal has the ability to lose their 4s electrons, but also lose some of the d electrons to get a stable charge as well. Okay. For example, if you look at Fe, iron, it's 4s2. Okay. Wait, hold on, 3d6, sorry. 3d6, okay? And so it goes 4s2, sorry, not enough blanks, 3d6, okay? So like all transition metals, you can first lose these two and become a 2+ charge. All transition metals have a 2+ charge or a +2 oxidation state when you lose the 4s. But what other charge might iron have to gain some stability? What else could iron do, looking at this orbital diagram, could it do to gain stability? Daphne? Exactly. It could lose not only those two, but it could also lose this one right here to form a 3+ charge. Exactly. Because a half-filled sublevel is a stable sublevel. So this is why iron has a 2+ or 3+ charge, and that's what we consider variable oxidation states. I guess I should write it as +2, and because I'm talking about oxidation states, I should write this as +2 and +3, because oxidation states, the number goes last. So let me write this here. So oxidation states. Okay. So the partially filled D sublevel allows elements to lose electrons past the 4s and still gain stability. Okay. Questions about that? Okay.
So yeah, why is a half-filled sublevel stable?
Because a half-filled sublevel means that there's one electron in every orbital of the sublevel, which means they're all spinning so that you minimize repulsion because everything's perfectly balanced. So you either want a full, empty, or half-filled. Those are your 3 stable states. Yes, Cass? Oh, whenever you name ionic compounds that include transition metals, you have to include the Roman numeral that says the oxidation state. Because if you gave a name of iron without saying iron 3 or iron 2, you wouldn't know what charge the iron was.
So is it iron 3 that's in the 3?
Yes,
If it's iron 2.
correct. Yes. So when you call it an iron 3 compound, you're saying that's iron plus 3 oxidation. So you should make your formula according to that.
Would you like, is it obvious to spell that, or is it?
In the name itself?
Well,
Oh, in the
when you
formula?
show it, will it show the formula and then you have to take it from that? Or-
Yes. Like you'll always be given one or the other. If you're given the formula, you can deduce the name. If they give you the name, you can deduce the formula. But you're not gonna have to guess, if that's what you're asking. Yeah, you're not gonna have to guess. Okay. The second characteristic, magnetic properties. Okay. This actually has to do with unpaired electrons creating a magnetic field. Okay. And so any transition metal is going to have partially filled d sublevel, which is going to cause unpaired electrons. This is why iron, again with 4s2 3d6, has unpaired electrons here, which means it can be attracted to a magnet, or it can gain magnetic properties. Okay, this is called paramagnetism. Okay, I don't know if we need to go that far into it, but the term for not having a magnetic field is diamagnetic. I don't think so. I don't see it stated specifically here, so I'm not going to say that, but I'm just going to mention para because it means unpaired electrons, just in case it gets brought up.
Wait, how do we compare electrons to magnetic field?
Because when they are spinning on their own, they create a magnetic field, and there's no opposing electron to cancel out its field, so it generates its own field that way. So if everything's paired, they all cancel each other out, Mateo. It's when you have unpaired ones that are able to spin freely, they generate a magnetic field that's
And I guess
unchecked.
the entirety is because, what is the magnetic field?
Wait, what do you mean?
Okay, so we're talking about magnetic fields to like, what is it?
Magnetic field is just attraction for like magnets and things like that. So acting as a magnetic or being attracted or repelled by a magnet. So those fields interact with each other. That's why iron can be pulled up by a magnet, right? Because it has the ability to attract a magnetic field. Okay. Okay. Complex ion formation. That's another characteristic. A complex ion consists of a metal ion and a ligand. Okay. A ligand is a species with a lone pair of electrons. Sounds familiar? It should. That's the same idea as with a nucleophile. A nucleophile is a ligand. Okay. No, you would usually want to use ligand in the context of transition metals, like complex ions. So they do have their appropriate scenario to use. So what is a complex ion? A complex ion is an ion that is composed of these species bonded together. And what happens is this. Chloride, Cl minus, is a ligand because it has a lone pair of electrons. And what happens is they each donate an electron. They donate their pair of electrons to form a bond. So this is a coordinate covalent bond. Okay. So chlorides are donating their electrons, Cu's accepting, which means that chloride is a Lewis base, and the metal is a Lewis acid. Okay, because yes, Mateo.
C2 plus. Wait, never mind.
The reason why it's a complex ion, Mateo, is because it doesn't bond like a normal covalent bonding does to form like necessarily like a neutrally charged octet. It's kind of special in that way where you make an ion, you make a complex that still has an ionic charge to it. So like what happens here is you see CuCl4, but because each Cl is a -1, this whole complex has a 2- charge. That's what this is. CuCl4 2-. That's a complex ion.
So if you ever write a gas structure, would you have to add the brackets and then put the minus outside?
I think usually just write it this way, but yes, you can do this as well. I think with complex ions, you generally just write it like this with the charge.
And then like the diagram.
Oh, this? Yes. Like that. Yes. Yes, Tifa.
So Cl is chloride? I mean Cl minus?
Yeah, Cl minus is chloride.
Okay.
So yeah, I think you missed this part because you were like getting here. But so whenever an atom gains an electron, like chlorine or oxygen or nitrogen, it becomes the ide ion. So when you name the negative ion, it always ends in IDE. Yeah. So chloride is Cl minus, chlorine is Cl neutral.
What about Cl?
There's no such thing, but I guess it would be like chlorium, I guess, because usually positive ions end in IUM. Yes. Yeah. So this is an example of a complex ion, an ion where it's forming this metal with these ligands that are attached to it, forming this overall ion here. But you also have to be able to figure out the charges and things like that in a structure as well. And so, for example, if I give you something like this. Oh yeah, sure. Here. Okay. Let's say I give you a compound like this. Okay, K3FeCN6. That's a neutral ionic compound. This is a complex ion. Fe bonded to Cn, 6 of them. What do you think the charge of that complex ion is based on the formula of the substance given? K is +1. It's B3-, right, Tifa? So this whole complex is FeCN6 3-. Correct. But within that, you should be able to figure out the charges or oxidation numbers of everything else within that. Okay? Because there's 3 Ks, right? So if K is 3+, then the rest of it has to be 3-, so it's neutral. So, well, there's no charge there, so yes, it's implied. That's okay. Cn is one of those polyatomics you need to know. Okay? Does anyone remember the charge of Cn? Yes, Daphne. -1. Okay? And there's 6 of them, though, so that's 6-. So what would iron's oxidation number be here? +3. Because it has to add up to 3 overall. Do y'all see where I got that? Because Cn is -1, and there's 6 of them, so that's -6, but it has to add up to 3- overall, so therefore iron would be +3. Does that make sense so far? Questions about anything? Okay. Would it make you feel better if I told you that was the kind of the hard part of it? Okay. Yes, Daphne. Yes, but you'd have to know the charge of that as well. Yes, you would know those charges. You should know like almost every charge in there other than the complex ion. Yes. Yeah. Okay. This thing is the kind of bigger thing here. Okay. I think it's easier, but I think it's the bigger concept here. This is 13.2. So everything we just did was 13.1, and now we're talking about 13.2. Why are compounds colored? I'm sorry? Yes. Okay. One of the things you need to understand is the reason one of them is because compounds can absorb certain frequencies of light. And reflect the rest, which is what you see. Okay. So when a transition metal compound looks orange, it's because it's absorbing the opposite color of light in its compound. Okay. So this is all about, you're not emitting any colors. You're not giving off colors like the hydrogen emission spectrum where you see like those lines. No, you are seeing the light that's passing through that's not being absorbed. So colored compounds don't emit light. That's not what it is. It just reflects the light that's not being absorbed. Okay. So this is where our color wheel comes into play on our data booklet, for those of you that have seen that section, because we talk about complementary colors here. Okay. Red, orange, yellow, green, blue, and violet. And so you see the complementary color of the color absorbed. So if I see orange, it's because my compound's absorbing blue. If I see violet, it's because my compound's absorbing yellow. That's what I see. And so this color wheel is given to you in your data booklet. Okay. So, well, why do these colors get absorbed? Here's why. Okay. Colors are absorbed because the partially filled D sublevel gets split when bonded with ligands. Okay, and once you write that down, I'll demonstrate what I'm talking about. So in a normal atom, all of the D sublevel are the same energy. Okay. For example, something like this. But when a ligand comes in here and brings in repulsion, ligands bonding causes repulsion. it actually causes these d orbitals to split in energy. And so what happens is they become something like this. They're still the same average energy overall, but now there are some that are a little bit higher and some that are a little bit lower. And now the electrons fill in here. Now, what it turns out happens is that when light passes through, this jump here from here to here is just the right distance for visible light to be absorbed. So what you might see is red absorbed so that the electrons jump up. And what's being seen is the green light that's not passing out, that's not being absorbed by that transition metal. Yes, Mateo?
Oh, wait, what happened? Why do we have two, like, levels?
Because when the ligands come bonding with the transition metals, those electrons from the ligands cause repulsion of the d sublevel. And the d sublevel splits in. They're usually 5 the same energy, but that extra repulsion gives some of the orbitals higher energy and some of them lower energy.
And why do they all accumulate in the bottom one?
Well, because remember, electrons fill the lowest energy orbitals first.
Right.
So what happens here is, the things you want to focus on is this, okay? A split d sublevel occurs when ligands bond, and what happens is, when light passes through the substance, the electrons absorb certain frequencies of light to jump up. And the frequencies that aren't absorbed, you see as color. For example, copper sulfate, CuSO4. Copper is a transition metal. And so when it's in water, water ends up being the ligand that bonds to the copper to make a complex ion. And that complex ion is what makes this appear blue. So in copper, in this copper sulfate, this complex ion is absorbing orange and you're seeing blue. That's how this works. And so the copper's sublevel splits up and it absorbs orange, which allows us to see blue in this solution. Now, if we added different ligands, it would change the color. And we're going to talk about that in a little bit. But ligands do affect the change in color here. Yes.
Okay, but if you see the light, that's supposed to be energy that is emitted, but
No, it's not emitted.
it's not emitted?
No, no, no.
But then why do we see like energy?
Because what we see is the color that's not being absorbed. Because what you imagine is white light's going through, and white light is all the colors of the rainbow, right? Well, the element itself absorbs the orange. So when light passes out, you see the blue.
This is reflected.
Yes, it's just reflected. Don't ever say emitted. It doesn't emit light. Like if you put it in the dark, you're not going to see any color. It only shows color when you're exposing it to light. Alexander, question? Oh, I saw your hand up.
So like the hydrogen emission spectrum, that will actually light up.
Yes, that actually does emit light. Right, Tifa. So hydrogen emission spectrum, you're giving energy, so much energy into the hydrogen that the electrons get excited and they emit light. And that's what you see. Yes. But here, there's no emission of light. It's just absorbing and reflecting. Okay. Now, one of the last things here, okay? The factors that affect the color reflected or observed, if you want to think of it that way. Okay. Okay. The three factors are as such. One, the metal ion itself. The identity of the metal ion is one of the factors because that affects how many protons are in the nucleus, which affects how much it splits. Okay. The more and more protons, the less it splits because the greater attraction. So the greater attraction, the less split. 2, the oxidation number. Okay. The more positive it is, well, actually, I have to kind of be careful about that. The oxidation number affects the split here as well. I don't believe there's I don't want to say a general trend here, but it affects the splitting, affects the split. And last is the ligand, okay? The strength of ligand, is listed in the data booklet. Yes, Mateo.
What is the split that we're talking about?
The split of the D sublevel, this, which is what determines what color you see.
So is that like how far apart they are?
Yes, how far apart they are, because the further apart they are, the higher energy color that it's absorbed.
And it's always divided in 3 and then 2.
Yeah, for our purposes here, yes. So let me kind of write down what Mateo said, okay? The larger the split, the higher energy color is absorbed. Okay, and don't forget, it goes Roy G. Biv. So lowest energy is red, highest energy is violet. Okay.
So we don't have to know how each one of these factors will affect the color reflected. So we have to know like if it's stronger, that's one of the ligand like going to do this and this.
Yes, I would know a little bit more about that detail. So the stronger the ligand, the greater repulsion, which means the bigger the split. So when you go to your data booklet here, let me go to data booklet here. Where is it? Okay. What you see is this. Okay. This is a list of all the common ligands here from I minus all the way to Cn minus and Co. These are common ligands for a complex ion. Okay. And Co is the strongest attraction to ligand. Okay. And I is the weakest. So the stronger the attraction for it, the greater the repulsion, the higher energy color absorbed. Okay. So if you're looking at I minus, that's going to absorb the lower energies of color like red, orange, and yellow. So you'll see blue and violet and things like that. But up here with the NH3, the Cn minus, and the Co, that absorbs more of the higher end colors like green, blue, and violet. So you'll see more red and orange in there as well. Okay. And so that's the main idea I want you to take from this is that the greater the attraction on this list, the larger the split, which means the higher energy is absorbed.
And what did you say that the oxidation number doesn't have like a fierce?
Well, it kind of varies a little bit, but let me double check something really quickly because before I speak out of turn on this, because I want to see something really quickly. Let me freeze this really quickly. So, because it varies a little bit, but I want to make sure I'm saying it. If there's an actual trend, let me double check something really quickly. For some reason, let's see. Where is it? Oh, here it is. Check something really quickly. No, not that. Double check something really quickly. Because maybe I'm speaking. Hold on, sorry, give me 1 second.
Ready for that or?
No, there's not a specific trend here. I was trying to see if there was a trend or something like that, but no, you just need to know that it changes it. It affects it. So I wouldn't worry about that.
So what kind of question do we have for?
So with this, it's not necessarily an oxidation number thing. They would probably ask you like state 3 factors that affect the color of the complex ion. So you would just state like the identity of the ion, the oxidation number, and the ligand. The type of ligand would be that. Okay. Okay. I forgot this term. I was looking at it here, but I forgot to write this in here, but I'm gonna do a couple more things and then we're gonna be done. Okay. 1, coordination number, okay, is the number of coordinate bonds present. So how many times does it bond to the complex ion? So example, CuCl4, 2- has a coordination number of 4, because there's 4 pairs of electrons bonding to it. Yeah, so when we look at this diagram right here, Tifa, the coordination number is based on, okay, how many pairs of electrons are actually bonded to it. And so this has 4 Cl's bonding to it with each contributing a pair. So the coordination number on the copper would be 4, because there's 4 coordinate bonds with it. Okay. So for CuCl4, it would be a coordination number of 4. It depends on the complex ion itself. You don't need to memorize like Cu is 4 or stuff like that. It depends on the ion itself. So you would determine it for each complex ion they gave to you. They wouldn't ask you to say what's the coordination number of Cu. Does that make sense? Okay. Yes, you can. Yes. So like if you had something like this, let's say you had Fe H2O 5 OH, something like that. And this was like 2+ or something like that. Well, the coordination number of that iron, it has 6 different groups bonded to it, right? 5 waters and 1 OH. So that would be a coordination number of 6. Does that make sense, Daphne? Okay. The last thing I want to say is this. Zinc is not a transition metal because it doesn't fulfill the requirements of its ions. It does not have a partially filled D sublevel. Oops, sorry.
Yeah.
Oh, it's also scandium as well. But zinc is the only one that's kind of listed in here, but scandium is technically as well too. But zinc is the main one you need to focus on. Okay. Scandium also doesn't have any partially filled D sublevel when it becomes its most common ion. So it's kind of tricky. The old IB definition said both scandium and zinc, but this new curriculum only says zinc, so I'm focusing only on that. Does not have a partially filled D sublevel as an ion. And does not, form colored compounds. Okay. Like when you think of zinc oxide, the stuff you use like for kind of sunblock, it's white. Their zinc compounds do not have any color to them. Okay. That is it for topic 13. That is the entirety of topic 13 in a nutshell. So I'm going to stop recording now.